So let me make sure that the recording is on here. All right. Okay, we should be good. We should be good. All right, so the purpose today is to give you an opportunity when you talk with your friend to say, I got one lecture at USF on how to be lazy. Okay, that's the whole goal of this lecture. Appropriately enough, it might be actually a shorter lecture than usual, so this is perfect. So we mentioned already lazy evaluation, right? And we kind of implied that this was, well, one of the hallmark, of functional programming, one of the benefit, one of the things that makes functional programming interesting. So we're going to dig a little bit deeper in that, okay? Just look at what features Java 8 offers that would be considered, lazy, and what kind of use cases we can leverage them for, all right? So, little quote to start the lecture. It's actually something that's worth thinking a little bit about. By the way, the guy that is on this slide, Venkat, is an absolutely must listen to on YouTube. Okay, so look him up. As a matter of fact, this lecture is going to be based on one of his books. Okay, it's really worth your time if you want to keep up with Java to listen to what this guy has to say. He has a lot of experience, I think 30 years something, and he has a very, very clear way to introduce those topics. Okay, so really worth your time listening to. So, what are we going to cover more specifically in this lecture? We are going to start by looking at things that are already there. Okay, things that we can achieve without streams, without really Lambda functional programming features. So we are going to look at delayed object initialization. How can we make sure that we can create very fast some objects without having to go through the whole cycle of initializing them fully? So that's going to introduce the concept of delay, right? I want an object right now, but maybe this object is not fully constructed yet. Okay. Then we are going to look at how to apply this, generalize, extend this to parameters, method parameters. So we're going to look at what Java does with its method parameters and, take a closer look at what happens when we inject Lambda there. And it's really interesting because automatically that allows you to delay the evaluation of code. And that's going to be something that we're then going to apply and leverage for the last two items of that menu. Okay, we're going to immediately jump into lazy stream. After that, we're going to revisit streams. The concept of intermediary operation, terminal operation, and look at how exactly Java 8 is processing those streams in terms of how do you optimize the processing. And I already mentioned that, like briefly, in one of the previous lecture. We're going to look at an example, make it crystal clear, and then we'll move on. And the last thing we're going to talk about, which is an interesting use case, an interesting example to illustrate, what you can do with lazy evaluation. We're going to talk about infinite collections, infinite streams, so series that never end, but yet you can process them and your computation will end. Okay, well, that's enabled by those tricks that we are going to cover all along, on lazy evaluation. So like I mentioned, this particular slideshow is based actually on one of the chapters of this functional programming in Java book. I really recommend that you look it up at the library or something like that if you want to, to have something to read that really matches the slideshow, the lecture. And again, this is from Venkat, so very good author, very good presenter actually. All right, so let's start being the good kind of lazy and talk about delayed initialization. So we're going to take a simple example, okay? We have a public class and we call it not so heavy because creating an object of that class doesn't take a lot of effort, okay? So what we have in that class, we have a constructor, not so heavy, and all it does is say, well, you just created an object of class, not so heavy, okay? Easy peasy. And then we have a toString method that we override from object, and it says, well, this is my object that's not so heavy, so we display not so heavy. So nothing really transcendental there, okay? we use that class, we create an object of class not so heavy. Let's say, 27.5, whatever, I don't know why, but 27.5 milliseconds go by, and the JVM has actually allocated memory for that object, initialize it. Well, in this case, I don't have much to do, but let's say, let's throw in a couple of fields, and let's initialize them to value passed to the constructor. All of this is done. And then, I can start calling method on the object immediately. For example, I can call toString. So, it's a trivial object, okay? But this is just our starting point, and then we're going to build on that, okay? It's a very trivial object, but it illustrates one of the fundamental, let's call it an axiom of object-oriented programming. When you create an object, by the time your object is created and you have a reference on it that you can use, the object has to be in a consistent state. It has to be in a correct state, I would say. Okay, that means fully initialized. No matter if it takes you 27.5, milliseconds, or if it takes you 5 hours of querying, 50,000 databases all over the globe. It doesn't matter. Whatever you put in the constructor has to be sufficient to guarantee that internally your object has a valid, a coherent structure. Okay, you cannot have dangling null references and missing initialize fields, okay? That's a fundamental thing in object-oriented programming, and as the program goes, we keep mutating the states of our objects. But we always try, to maintain a consistent, a coherent state at any time in our execution. And sometimes you even enforce that. Some of you might have heard about invariant, class invariant, method invariant, things like that. These are checks that you can actually introduce in your code, and you disable them when you go to production to speed up things. But while you are still developing and debugging, you can add those checks in your code to constantly pretty much double and triple check that, the state of your object at any point in time is consistent. Okay? So that's, again, we always do that. We take trivial code, but that code is enough to, capture one aspect that we want to discuss. Arguably, this is the essence, of any scientific method. So, now let's move on. Let's start making it a little bit more interesting. So, first let's discuss what could go wrong with this approach. So, we have the same, the same structure, but this time we call our class heavy. So that makes a hell of a difference, right? Well, not really, but by calling it heavy, we're going to assume that this time constructing the object is going to take a significant amount of time. For example, let's say 5 hours. Again, arbitrary number, okay? So this code is not going to take 5 hours to create an object. I agree. All right. I'm just saying that, let's say that we have a class heavy where the constructor actually does something more than just a system.out.println, and this operation takes 5 hours. Okay? So we have something like that here, and we are stuck. We are stuck in the execution of our code for those 5 hours. We cannot do anything with that object. And that makes sense, right? This is one of the rules in object-oriented programming. You create your object. Once it's available, it has to be perfect. Okay? But then again, there are things that we could do with an object that is not even perfect. Okay? So in this case, do I really need to have a long initialization just to be able to call toString on that object? And the answer is probably not. Okay, certainly not in that example, but that example is oversimplified a bit, okay? But there are some methods that you might be able to call on an object, even an object that requires a lot of work to be fully initialized. And those methods are maybe just using a couple of fields that are initialized in 1 second. So let's say you have like half of your fields that you can initialize in 1 second in the constructor. And then for the other half of the fields, you're going to have to put in 5 hours of work. If you just want to display, for example, an ID or the name of your object or something like that, you could probably do that without waiting the 5 hours. Okay? Or it's not even a matter of probably, it's a matter of there are some cases where you would be able to do that because of the nature of the object and the nature of its structure and the initialization work that is necessary. So in this case, we bar ourselves totally from ever being able to do that. All right. So other things that we could do is you have an object. The subject is not fully initialized. Okay, so I cannot use it right away. But maybe I need to pass it to other objects. And those objects, as part of their initialization, just need to actually record a reference to that heavy object, store it in one of their fields, and just store it in one of their fields so they can use it later. What does it mean later? Well, maybe that object is going to use my heavy object only 5 days later when a user clicks on a button. Okay? So why would I make that other object wait 5 hours to get a reference on my heavy object when I could just, put like an empty shell for my heavy object, give the reference to that other object stores it, and guess what? If the user clicks the button right away, yeah, they will have to wait 5 hours. But most likely, they're not going to do it for a day or two. So my other object, my heavy object, is going to have time to initialize, etc. But I didn't make the other one wait. So there are situations where that fundamental rule of object-oriented programming should be a little bit more flexible, or could be a little bit more flexible. Okay? So how do we make that happen? Let's look at a purely object-oriented programming solution. So we do not mess around with lambdas. We certainly do not have any stream yet. None of this is going to apply to stream immediately. So we are just trying to address that problem, okay? And again, I'm using simplistic, oversimplified, you could argue, code, just so that we don't have like a ton of code to go through. But the idea is that we always assume that in the class heavy, the initialization is something that's, heavy, okay, time consuming. All right. So now we have another class that we add to the mix. We call it naive holder. So that kind of implies that there's going to be a better solution coming up very soon, okay? But for now, that's our first attempt. So the public class naive holder has a field, a private field of class heavy. So that's going to be used to store a reference to an instance of an heavy object. So look at the naive holder as a sort of a wrapper around the heavy object. Okay, so instead of just creating heavy objects, now we're going to create our naive holders object, and those are going to kind of manage the processes, the cycle of creation of the heavy object for us. Okay, so that's the big picture. If you look at the naive holder constructor, it's just going to allow us to kind of debug, and see what's happening in the screen and what order operations are done. So we just do a system.out.println. Pretty much it says holder created, which means, you are running right now the constructor of the naive holder class. Okay, just for us to see what's happening. And then here's the interesting part. So that naive holder, I told you, is kind of like a wrapper, right? It's our intermediary between us and the heavy object. So one of the methods that we're going to provide, one of the instance methods we're going to provide in the class naive holder is get heavy, which means give me my reference. Okay, you're supposed to be in charge of creating those heavy objects. I want one right now. So what do you do in that method? You do pretty much just-in-time instantiation. And it's not a technical term, it's just something I made up, okay? But that means that when you call the getHeavy method, you say, I want my instance. Maybe you constructed your naive holder 5 hours ago, all right? But you didn't need your instance. So you could pass that reference to your naive holder object to everybody who needs it. The bottom line is the first time somebody, meaning actually a method, so some code, the first time some code in your application is going to call getHeavy because they actually need the instance, then only then we're going to trigger this code. And this code, what it does is, it's kind of like reminiscent of the singleton class, right? The singleton design pattern, sorry. The first thing I check is, what is my field heavy? Okay, I'm the holder, so what's the status of my field heavy? Well, if heavy is null, that means I never created yet the instance. I was waiting, okay? I was buying time for other part of the code to spread me around, for example. So if it's null, then I assign to it a reference to a new heavy object. So I finally do the work to create an heavy instance. And then, whether or not I had to do this, I return heavy. So the first time you call that method, just like with the singleton design pattern, the first time you call that method, it's going to create an instance. Afterward, it's going to just return the instance that was created the first time. And we're done. Okay? So it's relatively simple. It's a cheap solution. We didn't use any new concept. It's just a good old-fashioned OOP. But you can see that we successfully delayed the creation, the full instantiation of an object. And we allowed the code to pass around a reference to the holder just so that other objects can initialize themselves and say, okay, I'm going to keep a reference to that heavy object. Well, actually, you wrapped it around in a holder, so I'm going to keep the reference to the holder. And only when you need it, you create it. That's being lazy. That's waiting. I don't know if it's so much lazy or procrastination, but I mean, the two are kind of related anyway. But it's wait that you have to do something to actually invest the time to do it. So here's how we would use this solution. So we say, instead of saying I want a heavy reference, we say I want a naive holder reference named holder. Okay, I create a new object of class naive holder. I'm going to display on the screen, okay, I'm deferring the heavy object creation, just so that we put a marker on our display that separates the creation of the naive holder from the creation of the heavy object itself. And then I have two system.out println to finish this code that just call getHeavy on holder. So I need the reference. I need it twice. Okay, and since I passed that reference to println, guess what? We are going to automatically invoke, toString on it and display whatever toString displays on the screen. So if we run that, we get the following. I mean, you're all expecting it, so I don't think there's any surprise. When we create actually the object of class naive holder, the constructor of naive holder displays, the holder is being created. Then we display that system.out.println, that is right there on the line, on the second line. So deferring heavy creation. Then the first time we call getHeavy. GetHeavy calls the constructor of the heavy class. Okay. So heavy created. That's from that constructor. And the second, when we call getHeavy, so the constructor is triggered and then the toString method is triggered. Okay, because we pass immediately that new object to println. And when we call it a second time, well, we bypass the constructor, so there's no need to reconstruct the object, it's still the one object, right? So we just jump immediately in the toString method. Okay, so that's a relatively successful pattern. Okay, all we did really is we did something that we kind of do also in other design patterns, like for example the decorator design pattern. We introduce aggregation here. Okay, we say the holder contains an object of class heavy, and then it acts like a manager, a superset of what the object of class heavy does. So that illustrates also, just a side note in passing, that illustrates also one of the great dilemma of object-oriented design, which is, do I use inheritance or do I use aggregation, composition? Okay. The trend was, when inheritance was new, everybody wanted to do inheritance. I fell for that too. The trend nowadays is more to say, okay, stop, think. Inheritance is great if you have things that you want to structure at compilation time. Okay, but if you have things that you want to structure at runtime, well, then composition is a little bit more flexible. Okay, so here we might have been able to do that, with inheritance by just having naive holder inherit from heavy. Okay, but we have a directly more flexible approach here by just using composition. So it's great, but it's not really great. There are problems with this that some of you might already have, floating in their mind. The main issue with this approach comes with its interaction with concurrency. Okay, so it's a rec. It opens the door to race condition. So we're going to look a little bit more in detail what I mean here. So in this setup, what we are trying to do is we have a reference variable named shared of class naive holder. Okay. And then we create a naive holder object, put the reference into that variable. We do that when we start our application, so when there is one thread executing in our application. Then we create two threads. Okay, we allow those threads to both access actually the shared field. All right, so that's why we call it shared. So what you see is the first rectangle is actually what happens before creating the thread, and then each thread has its own rectangle of code. And in that code, what we are going to do is we are going to call getHeavy on that shared object. Okay? So we want the same benefits. We want the ability that the first call to getHeavy creates an object, and then every other call is going to just return the reference we created. We don't want to create two objects. We don't want to forget to create the object at all. I mean, we don't want any of that nonsense, okay? We want the same thing to happen here, but because we have concurrent calls to the same method on the same object, we are going to have issues. So let's take a look at what kind of issues we are going to get. Okay, so those of you who are familiar with race conditions, you're going to recognize an archetypal example here. So this green arrow is going to tell us what we are executing. Okay, so yes, we have already that shared variable. Now we're creating the object of class naive holder. So you can see on the console here we get holder created. Okay, and then I didn't put it here, but let's assume that we have that system.out.println that say, okay, I'm deferring now, you know, the creation of the AV instance. So all of this is done in the upper rectangle up there, okay, before we actually go multi-threaded. So we are going to get rid of that rectangle now and focus on, well, let's say thread number 1, okay. So we assume that execution starts at thread number 1. Thread number 1 goes for the next step in the code, which is I have a variable h1, and I try to put a reference in h1 that is given to me by getHeavy from the shared object. Okay, so we execute, we call getHeavy. The first thing that getHeavy is doing is that test. Okay, if the field heavy in the shared object, okay, is null, then I need to create that thing. And unfortunately for us, testing heavy equal null and then executing the body of the if statement is not a transaction. It's not a transaction. It's not an atomic operation. We didn't define any critical section that had to be uninterruptible. So that means that Murphy law tells us that if something can happen, it will happen. And what happened is that we pass the test, so the condition is true, and then immediately we switch execution to thread number 2. All right. Now we are in thread number 2. Thread number 2 is trying to do the same job. So it gets into the method getHeavy on the same object. It tests heavy is null. Well, yes, it's still null. Okay. I switched to thread 2 before thread 1 had a chance to actually assign anything to the heavy field. So that means that the test is as true as well, okay? And so therefore I go to the next step, and well, that's scheduling for you. I keep executing. So I execute heavy equal new heavy, create an object of class heavy. So on the console I'm going to see that heavy has been created. So that's the constructor talking there. I complete that operation, and then scheduler switches me back to the first thread. Okay? I resume execution where I left it in the first thread. That was right before to call heavy equal new heavy. So now that I resume execution, I can go ahead, all right, and I create another heavy object. So you can see the problem now, all right? I had created 2 heavy objects. Even more interesting, since I hold only one reference, right? The first heavy object was created, I kept its reference. The second heavy object was created, its reference overwrote the previous reference. So now, not only I have this race condition where I created 2 objects where I really intended to ever create one, but I have a reference now in thread 2 that has been assigned to the, well, now it has been assigned to heavy, so it's not going to be that bad, okay? But if I had that reference and I was using it for other stuff, passing it to another method, that reference would be a big problem because it's a reference to the first heavy object we created. And by all account, when you are going to keep using your naive holder object, every time you ask for a reference, you are not going to get that first reference. You're going to get the one that won the so-called race condition, the second reference. So half of your code is going to operate consistently on an object, okay, of class AV, and then a little part of your code maybe, or the other half of the code, is going to operate on another instance of AV that has been long forgotten, okay? That's the problem with concurrency. This can be a real nightmare to debug. Programmers that are not actually well versed in concurrent programming technique which is probably the majority of programmers, okay, let's be honest, we can write that kind of code and think that it's okay, all right? But at the end of the day, it's not. But the bugs are going to manifest themselves in a transient manner, which means that you run that application, that little program, 50 times, one time it's going to bug. So you immediately tell your colleague, hey, I have something weird here. The colleague comes, runs the code, say, no, your code is working. So you cannot, with concurrent programming and that kind of bugs that are based on scheduling, timing between threads, you cannot easily reproduce bugs. That's part of what makes them difficult to find. And if we use the example that I mentioned, where we even leak that first reference to the first heavy object that was created, we leak it somewhere else in the code, then figuring out that the same code that is perfectly working on one reference doesn't work on the other, and tracking back, down where that reference first appeared and why it appeared, that can be actually a lot of manpower dedicated to just debugging very simple code that was written too hastily. Okay, so that's one of the motivation also for functional programming, is that this is one of the most elementary bugs you can encounter in concurrent programming. Okay, there are others that are less, straightforward. So imagine that if this one can still sneak in your code and surprise you, the ones that are much less straightforward are going to actually surprise most of the developer in a team. Okay, so that's why we are taking an approach for the last 5 years, 10 years, I don't know, that is, let's try to avoid situation where we can potentially introduce those bugs. Okay? You had a question?
It's more of like a remark. In this case, I just want to know, after the if is executed, you say that the thread switches, the scheduler switches the thread, it goes to the second thread where H2 OB, it's called, we're trying to pass an instance of heavy to H2. So just as a solution, if I wanted a solution, a simple solution, could I have, like in my native holder class, could I have instant kept like a flag to check whether execution has started, and then if it started, then okay, don't start executing. Yep.
So
I just want to know.
Yeah, so that's a good remark. So the remark is, well, okay, so I have a problem, I have concurrent access to the shared variable heavy. So it all works that way because, I cannot keep track of when I started that if statement. So what I'm going to do is I'm going to introduce another field, in that shared object. Let's call it flag, okay? And before to actually commit, to create my new instance, I'm going to check my flag. And my flag purpose is just to tell me whether, I already entered one of those if statement. So the code would look something like, if AV equal null, set your flag, okay? And then if your flag is set, then heavy equal new heavy, okay? That's fine. That's fine except that, forget about heavy. Look at flag. Flag is a shared variable, right, between two threads. And what you want to do is you want to read the value of that variable, test it, and then if it passes a test, you want to do something else, okay? Does that sound familiar?
Is it semaphore?
No, it's not semaphore yet. Okay, we're not dealing with semaphores here. We are dealing just with a shared variable, right? So it sounds familiar because this is exactly what we did here with heavy. So the same window of opportunity that existed in the read, test, and then commit an action with the heavy reference exists with the flag reference as well.
My solution was, I was just thinking, if I put an if before checking heavy equals null, I mean, if the flag is false, set it true.
Mm-hmm. So, okay, so
and flag is true.
Next version is do not do the if heavy equal null first, do the if flag equal true first, then set it. Same problem. You check something. Okay, the essence, we are going to go over it in more detail next lecture, okay? We're going to try to do a kind of a refresher on concurrent programming. But the issue is always, you read the value of a variable, you test that value, and while you do that, you can be interrupted. And the value can change in another thread. And then as soon as you're done and you resume, you go ahead proceeding assuming that your variable is fine, but it's not. Yeah, question?
Small remark about this conversation. So, as I know, there is like in processors, there is instructions that performed atomically. So it's like interlocked functions. So we can actually perform this test introducing interlocked like variable that we can atomically increment or test. So actually, there are API to do so, but with usual syntax, it's not possible.
Okay, so the remark is, hey, processors have actually in their instruction set, something to allow you to test and set, registers or whatever atomically. Yes, that's one of the solutions. So when a programming language allows you to use atomic values, for example, the Java programming language allows you to use atomic int, atomic long, stuff like that. So the guarantee is that when you access those, when you assign those values, etc., it's going to be an uninterruptible operation, and atomic, that's what it means, unbreakable, cannot be subdivided, in smaller parts. So yes, that's one of the solutions. There are other solutions. There are purely algorithmic solutions like Pearson algorithm, okay? There are also other solutions that are more, I would say, practical. So the atomic and the Pearson algorithm are typically things that we go over in the IT operating system course, okay? When we discuss about concurrency. But here what we are going to do is we are going to use features of the Java language that allow us, it's not going to be semaphores exactly like you were mentioning, because semaphores are a little low level, but there are features in the language that allow us to define a series of instructions as being like a transaction, pretty much. These needs to execute completely, all of them, or none of them. Okay, and that's the same transaction concept that is used in databases.
Yeah, continue this conversation. We can actually redesign. Yeah, you said that there are a lot of approaches, and one of the approaches is like idea of actors. Yeah, you know. So
yes, I know actors.
We have shared states. Yeah, like between two threads. We can this state we can give to just one thread, and the other threads should ask one thread for this state, and that state should be immutable. So it's kind of the pattern that is used in functional programming.
Yeah.
Another approach, do not use interlocked or share it like semaphores or mutexes, but use actors.
So the point was there are other approaches. Like, for example, if we go for an agent-based programming paradigm, we can actually pretty much encapsulate the state of an object and assign it to one of the agents, which is pretty much a thread, okay, a concurrent execution unit, and make all of the other agents, have to wait for that object to be freed. So it's kind of the same idea than a lock, it's the same idea than a semaphore, it's the same idea than a mutex, okay. All of those concepts revolve around the idea of we need to police access to things, okay. While I am doing something, while I'm modifying, for example, the heavy reference, okay, there are a few lines of code that I'm going to call a critical section, because I know that those few lines of code should never be messed up with by the scheduler. Meaning, I should never interrupt execution from the moment I start my if AV equal null to the closing curly brace. So the traditional approach to concurrent programming, okay, in OOP, is to identify with experience, with patterns, to identify those critical sections where you are modifying things that are shared, okay? And then one way or the other, using semaphores, using mutexes, maybe, using something more elaborate and higher level like agent, stuff like that, you are going to be able to say, I'm going to guarantee that these 2 lines of code or 3 lines of code here are never going to be interrupted. And that's the key. Okay. Now, the difference between, for example, using semaphore and mutex, which are considered nowadays, low-level solution to concurrency problem, and using something like monitors or using something like, actors or stuff like that, or the synchronized blocks that we are going to talk about, in the next lecture. Well, the difference is how easy it is for you as a programmer to not only write the code, but reason about the code. Okay, the lower level you go, the more stuff you have to keep track. Okay, for those of you who are curious, we are going to look at the producer-consumer problem, next lecture. But if you are really curious, look it up, a little bit ahead of time and compare a solution to the so-called producer-consumer problem. Okay, written in C using semaphores, and written in Java, just to see the difference. And you're going to see that there are less little details, less little bit of strings, that are fixed by taping them with duct tape, hanging everywhere. So it's just freeing you from the opportunity to introduce more bugs, and that's about it. So next lecture, I promise you, we'll go over that example again, okay, in a little bit more detail. We'll do a refresher on concurrent programming, okay? But for now, I wanted to just introduce here the idea that pretty much, well, that's the next slide, good transition. The idea that we have ways to defer object creation. And we have naive approaches that do not require, functional programming or anything like that. However, they immediately catapult us in the realm of you cannot easily make this code execute in parallel. Okay? And that's really one of the fundamental motivation for the last 10 years or so for this move, that we can observe toward, functional programming is not just something, computer scientists do during their PhD. It's actually something that, yes, it forces you to think differently, but there are benefits. There are concrete benefits that you can leverage in industry. So for an IT program, yes, that's the point where we can now go back to functional programming, introduce it to you because it's really relevant. So in this case, in this example, what we had was a race condition between two threads, okay? We failed to delay actually the initialization of the object. We kind of delayed it a little bit, but it's completely overshadowed by the fact that we allowed like multiple objects to exist. So that's actually not a feature, that's a real bug, okay? So even just for that, that's not an acceptable solution. So let's talk about more acceptable solutions. So I would hope that at least, a few of you are going to say, well, you used get heavy, after creating the threads. That's nice. Why didn't you use it before? All right. So in the code that we were looking at, it's simple code. There's no good reason for us to do this step, after creating the thread. So we could have done it before in this code. But that's kind of like a heavy constraint. For all the code that will ever work, what you are telling me is I can be lazy as much as I want, but as soon as I start multi-threading, there's no more laziness, no more lazy evaluation. So yes, in essence, we are saying, okay, lazy evaluation is impossible with multi-threading. Well, no, it's too strong of a claim, okay? It is possible, we just have to be careful, okay? So we are going to assume that, yes, we want, in the general case, okay, to be able to delay initialization past the time where we multi-thread our application. Okay, so it's a good thought, that solution one. Okay, always go for the easiest fix, but that just it comes with a price. Okay, it's too general of a constraint. The second thing we can do, and that's actually how you would do it as an object-oriented programmer. You are going to fix that getHeavy method, because getHeavy method is actually a critical section, okay, to use the jargon that we just introduced, okay? So you recognize it as a critical section, and then you take your favorite, concurrent programming shotgun, and you start solving the problem, as you should. Fortunately for us, Java is a good language. Even just the basic OOP version of Java is a very good language to handle multi-threading, concurrent programming. So we don't have to go into mutexes. We can go to atomic, data type to speed up things. But let's say that we're not trying to optimize. We're just trying to get the code to work, be safe, and keep our sanity. Okay. So we take the easiest approach. So we're going to introduce some sort of lock. Just putting the keyword synchronize. I don't know how many of you have used synchronize before in Java. Never? Okay. Well, it's very simple. It's very nice. You're going to see. So just using the keyword synchronize here is going to allow us to make this entire method thread safe. So safe for concurrent execution. Okay, so it's not really magic. Okay, the idea behind synchronized is, okay, some of you talked about semaphores. You know, we kind of got the concept that there is a need for a locking. Okay, your solution was, hey, I want a flag, and that flag really I should have called it lock. It's kind of a Boolean variable that says you can go or you should wait. Okay, so when you use a synchronized keyword, what happens is that on that object, okay, so the object of class, naive holder, okay, as soon as one of the execution thread calls one of the methods that have been marked as synchronized, then no other thread can call on the same object, the same shared object, can call another method that has also been marked as synchronized. So if I mark one method as synchronized, that means no two threads can enter it at the same time. So the first one that calls it enters it, and while it's working inside the code, even if it gets interrupted and the scheduler decides to execute another thread, that other thread, if it calls the same method, cannot enter it. It's going to be stuck there waiting for execution to complete. So it's kind of like the idea of that you were describing of actors, where, you know, one actor is busy modifying this object. Well, if another actor wants access to the object, it's going to ask, can I go in? Can I go and start messing with the state of that object? And the answer is like, no, wait, I'm not done. Same thing here at the level of a method. Okay? So that's it. That's what synchronized does. Now, if you have, just let me finish that and address your question. Now, if you have several different methods marked as synchronized, it just generalizes. That means that when one of the synchronized method is at work, no other method that has been marked as synchronized can be called by any other thread to work on that object. Okay? So that allows you to pretty much handle, I would say, 90% of what you and I are going to probably deal with in terms of concurrent programming. Yeah, you had a question.
Suppose one thread enters and it is getting stuck in the synchronized method.
Mm-hmm.
So then what will happen?
Oh, yeah, that's a good one. So let's say that you put an infinite loop in one of your synchronized method, or in your unique synchronized method there. What happens? Well, you just messed up. Okay, there's no nice way to say it. Once you start execution of that synchronized method, the first thread that enters the synchronized method is given a green light. It starts execution of the synchronized method, and if your synchronized method never ends, well, that thread keeps looping and, you know, displaying hello world, hello world, hello world, hello world on the screen. That's great. And any other thread that is trying to call that method, because of the definition of synchronized method, is not allowed to even start execution. So that's it.
So
You're done.
Like synchronized doesn't have any method that would kill the thread after a certain time, or suppose if it is.
Yeah, there are ways around that. I mean, like you are mentioning, you know, can I kill a thread, you know, after a certain time? Yes, you can. You can have another thread that's a monitor. Okay, that's going to actually make sure that there is the property you're looking for is called liveliness. Okay, and we are going to talk about it again next lecture. Okay, the idea of liveliness for concurrently executing program is: are we making progress? Okay, are we stuck, or there are different ways to be stuck? Again, I'm going to cover that next time. Okay, but one way to get stuck is to say, well, nobody moves. No thread can make any progress. I have like 50 threads that are actually waiting on some form of weird setup of conditions, and none of them is going anywhere. And then there is what is arguably, you know, the preferred hobby of mankind, which is getting busy going nowhere. Which means that everybody is working really hard, you know, but we're all doing stupid stuff, and we're all, you know, going one step forward, one step backward. So at the end of the week, you know, we're all tired, and we're like, wow, I did a hell of a week at work. And then you look at the result, there's nothing that got produced, okay? So that's our favorite pastime. But yeah, that's another form of, you know, losing liveliness, metaphorically and concretely. Okay, so it's we are going to go over the actual definition of those two problems. Okay, so next lecture. But yes, there are workarounds. There are always workarounds, and the workaround introduce new problems. There are workarounds to the problem. So what we're going to try to do in this lecture, instead of studying, you know, all those workarounds and how to work around the workaround, we're going to try to prevent those things from happening to start off with. Okay? Yeah, question?
Doesn't the JVM take care of it in a way, as in if the compiler kind of detects an infinite loop while in runtime or in compile time it just detects that okay, you probably might. What happens in JavaScript?
Okay, so hold on. Let me address this part first, and then we'll move to the second part of your question. So the question is, why isn't the compiler doing anything? And the idea is that, okay, that's okay. That's not my field, so I don't want to say that nobody ever tried to do something like that, automatic detection of deadlocks and things like that. I know there has been some theoretical research on trying to prevent deadlock by analyzing the code, detecting potential for deadlock ahead of time. Okay, I don't think this is a mainstream solution in the JVM. Okay, not that I've heard of. The idea is always, if you are looking at code analysis, there is a theoretical limit to what you can do with code analysis. Okay. A computer program cannot actually understand another computer program without executing it. So, for example, if you have that infinite loop, yes, it's easy to see an infinite loop. You know, while true, opening curly brace, closing curly brace. So those you can detect even at compilation time, okay? But the truth is that in any non-trivial program, you're not going to be able to do those inferences on what the code is actually doing. So the other thing you could do is to say, well, there's a timer, right? If my thread, is executing that method with that infinite loop that you were talking about, okay? Well, after let's say what, an hour, then something is wrong. Or 2 hours, well, maybe after a day. Or maybe after a month, because we have at research computing here on campus, we have people that actually send processing task on a cluster, and they expect the result, after 2 weeks or something like that. So then here comes the problem of, you cannot have a generic catch-all solution, that say, well, no matter the program you write, I'm going to detect if something goes wrong. Because that would be too difficult. But in a particular application, like I mentioned, you can introduce, some part of the code that are going to monitor liveliness of your application. Make sure that if you know that you should not wait more than 1 hour for completion of a task, yes, you can set up a timer, and in 1 hour, if that task is not completed, kill it, kill it dead and restart it, for example. So there are more or less, elegant solution to those problems. And like I said, it ranges from trying to analyze the code beforehand to actually just kill everything and restart it, check the box if it's not working. So, there are different workarounds, okay, but nothing that is one solution for all potential problems. What was the second part of your question?
Actually, in JavaScript, usually at times when coding, you just forget, and so there is an update method. You hit a listener, and in the listener, you by mistakenly you just add the update again. So in the first loop, at runtime it ends up throwing an error saying that okay, you're calling it infinite times. So that's why I was hoping, because this is pre-compiled and then run. So probably is there does it detect on runtime, or is it just going to run till I don't kill it, or do I have to actively set a monitor to check it, or is it just
my answer is still the same. You have, as far as I can judge, you have to set up your own monitor, because you cannot set a rule that's going to work for every type of task. Yeah, you had a remark too?
About, you said detection of the blocks, problem of detection. Yeah. Actually, SQL Server, for example, or other products, Oracle, perform such tasks, but it's more high level. So Java, it's more low level. You need to implement by yourself this kind of management. And in several products, they perform building the graph of dependencies, and then detecting the loops in this graph, and then queuing one of the transactions. So it's kind of similar problem.
So the remark was, in other setups, like other tools, you have this concept of I want to detect potential for deadlocks, and stuff like that by, for example, using a graph of dependencies. This task is waiting for that resource, this other task is waiting for also that resource, etc. So there's a if you ever read a book on operating systems, operating system concept, design principles, some introductory undergraduate text, you're going to probably find a lot of information about those problems. I recommend Andrew Tannenbaum. He's a well-known author for operating system textbooks and operating system research, and he had a joke that is actually related to what you were saying. In one of his books, he was saying that the point of trying to detect deadlocks by using graph algorithm, so make a graph of dependency and try to reason about that graph, was actually just a way to keep graph theorists, computer scientists in business, still have a job, okay? And he was himself doing research in graph theory, so I think we can take it from him that it's not a ill-intended, joke. But yes, there's a whole range of methods, from the most theoretical to actually the most practical, which is shut it down, start it again, okay? So, we are going to look at something a little lighter, maybe a little more complicated conceptually, but lighter in execution than full synchronization. And again, next slideshow, after Thanksgiving, we're going to talk about, what can happen with synchronization that goes wrong, when synchronizing everything can be actually a bad move. All right, so we do have an alternative, hopefully, based on lambda expression, based on functional programming. So let's revisit our holder, but this time we are going to have not so naive holder. We are going to have something a little smarter. So let's look at the easy stuff first. So public class holder, that's easy, right? Public holder, that's our constructor. System.out.println, the holder is created. Okay, we know that. Heavy, get heavy returns a heavy reference, returns heavy.get. Okay, that .get is new, but we have a heavy private field here, so we are pretty much returning the reference stored there. The part that is a little bit unusual, shall we say, is this one. So our heavy, instead of being a reference to an object of class heavy with uppercase H, now it's a functional interface. It's a supplier of heavy. So the functional interface supplier of heavy, simple. So all the functional interface I told you already previously, they just define, what your function looks like. Well, a supplier is a function that takes nothing. You just call it without parameter, and it returns something. In this case, a reference to a heavy object. So now when you look at the lambda, okay, maybe it makes a little bit more sense already. Our lambda that we assign into that variable, that field heavy, okay, takes nothing, and return a reference on a heavy object that is created by another method called create and cache heavy. So the weird thing about that is that when you first look at this example, it takes a few readings, okay, to really appreciate it and taste it and see exactly why it's so interesting. But the first time you look at it, you say, hold on. So instead of having a reference in heavy and creating it into get heavy, now get heavy is not creating anything. It's just deferring the problem on the shoulders of whatever I put in heavy. And whatever I put in heavy is a lambda. So it's not even executing right now, but whenever it's going to be called, it's going to execute, and the only thing it's going to do is call another method. So these are the things you should be struggling with right now, okay? Good news, after you read that code 5 times, that's going to start making sense, okay? But I'll run you through, slowly through one time. Ask me questions as you go, but it's going to take a few reading to get used to it, okay? It's a very interesting design, very elegant design. So, everything hinges really on the fact that we have a lambda, and that lambda calls this method. So let's take a look at this method. And when we said we are going to make things, I don't know if I use the word simpler, but that was probably a bad choice. It's conceptually more difficult. It executes better. That's the advantage, okay? So what do we have in that create and cache heavy method? Well, first, it's synchronized. Okay, so that means that this method is thread safe, no problem. The first thread trying to get into it, we will get into it. The other ones are going to have to wait. The second thing about this method that is interesting, well, we have an inner class inside of it. Okay, so remember when we talked about functional interfaces, I told you, well, that's kind of a way to avoid, lambdas are a way to avoid inner classes and stuff like that. So this code is going to hinge on the fact that this lambda that I assigned to the heavy field in the previous slides, okay, I'm going to be able to replace it by an instance of that thing if I want to. That's going to be one of the key that's going to trigger, the inner working of that approach. So what do we have here? Well, we have a class heavy factory, okay. So it's not an anonymous inner class. So we put a name to that one. You're going to see why, because we use the name here again. All right. So we have a class heavy factory defined inside this method. This class implements an interface. That interface is supplier of heavy. So that should ring a bell. That's the same functional interface that I use as data type for my heavy field in the holder. Okay? So an object of that class could be assigned to the heavy field and replace my lambda. That's the point. And then opening curly brace, so that's the notation when I want to immediately, provide the code here for my class. Okay? So my class heavy factory is going to be defined as follow. I have a private final field named heavy again. Named heavy instance. That's a reference to an object of class heavy. Okay? And I create immediately an object of class heavy. All right? And then I have a get method that I'm going to use here. Okay? And that get method is actually what allows me to claim that I fulfill the requirement of the supplier of heavy functional interface. Okay? Functional interface means, again, a class that has one method, right, that we can use, public. That's the method I need to be part of the gang of suppliers of something. So I need the get method. My get method just returns whatever I created here. So it's a very stupid class, okay? It creates an object of class heavy, stores a reference, and then you can get that reference whenever you call the get method. What's next? So that class is defined inside my method create and cache heavy. And then the next thing that my method does is attest. Attest if my heavy field in the older class, okay? Attest if my heavy field is actually an instance of the class heavy factory. So I just defined the class heavy factory here, right? By default, what is inside the field heavy? I put a lambda. That lambda is not of the class heavy factory, okay? It's just a lambda. It's an anonymous inner class that implements the same functional interface supplier of heavy. Okay? So the question here is pretty much, what's inside heavy? Is it the lambda that I put originally in it? Or is it an object of this inner class? So pretty much another, functional object that would be created by instantiating that inner class instead. So that's really the question we ask here. So if it's not an instance of this class here, heavy factory, so it's my original lambda, okay, then I replace it. So the first time I call get on the field heavy, I trigger my lambda. My lambda call this method. This method realize, hey, my good old lambda is what's in heavy right now. I'm going to replace it by an object of class heavy factory. I create an object of class heavy factory. That means that inside of it, I create an instance of heavy and I put it in there. Now that object is ready the next time you call get to return that instance. And guess what is the last thing we do in this method? Well, no matter whether I had to create an object heavy factory and replace my lambda, or whether it was already an object of class heavy factory, like the second time I call this method, for example, well, I'm going to just call get and get the reference. Okay? So a lot of intermediary steps to get there. So it should not be trivial, okay? Be reassured. And again, it's not that it's so fundamentally hard. You are going to go through it, you're going to get it, you're going to understand it, trust me. Okay? It's not, going to cramp your brain, like destroy your neurons. It's not that hard, but the first time you encounter it, it's that weird. Okay? It's not hard, it's weird. It's a very elaborate way to go around, etc. So trace through that a few times, post question on the forum, okay? It's normal that it's unintuitive. Anything worth learning is going to be unintuitive at first, okay? Question?
Yeah, about previous code. So it's the major effort, as I understood from this code, is to remove synchronized access for second and third calls.
Yeah.
So but just to make it the first time synchronized. and then we just receive this
for free. So yeah, the remark is actually very on the spot. The remark is, so all of that is so that we do not have to constantly go through that synchronized method to get our reference. Okay? The first time we have to create the reference on the fly, we do it in the safety of a synchronized method. But then the next time I call, get heavy in my holder, what I have inside the heavy field is no longer a lambda calling that method. It's going to be an object of the class heavy factory. And guess what? The class heavy factory has no synchronized method. So when you try to get, the reference from heavy factory, you call the get method from heavy factory, which returns immediately the reference. So the idea here is that we need synchronized, but we don't need synchronized all the time. The flow of our previous approach, our previous solution, was that no matter whether it was the first time you called get and you wanted to create that instance, or if it was the 50th time you called get and you just wanted to obtain an instance that already exists, you had to go through synchronize. That slowed down things considerably. Here, only the first call where you have to create the instance is synchronized to prevent all the snafus, that we discussed 30 minutes ago now, okay? But the idea is that once your instance is created, that was the critical section. The critical section was that if do I need to create the new instance? Yes, so let me create it. That was our critical section. That was where we had a race condition. So we encapsulate that in synchronize, and then all the other calls to get, you just want to receive a reference that is inside a variable. You cannot mess that up. You cannot mess that up with concurrent access. Why? Because the fundamental issue that leads to a race condition is updating a shared variable. If you have two threads that are trying to read the current value and then update it, there's a window of time between the read and the update. If you are interrupted, you're dead. Okay, race condition. But if you keep reading, that's it. It's like if you can have 50 million threads reading a shared variable, as long as it's read-only and there is no update, you can do concurrent programming, as much as you want. You don't have to use semaphores, mutex, monitors, and none of that stuff. It's going to just work very easily, okay? All right, so we're going to finish with the concept of lazy evaluation. Okay, so we already delayed evaluation of objects. Now we are interested in trying to delay evaluation for any method. Okay, and we're going to do a quick jump here through parameters evaluation. So this is something that already exists in Java. Okay, like for example, when you look at Boolean expression, when you say I call the method test on X, and then logical AND I call the method test on Y. All right. So the idea here is that there is something called shortcut evaluation. You call indeed the test method on X, but if the return value is false, there's no point in going and calling the method test on Y. Okay? Because the AND operator requires both to be true to return true. So if one is false and it's the first one, even if you have 50 other terms afterward, ignore them. You got a false, that's all you need. And the opposite is true for the logical OR operator, which is the second line here. If I call test and it tells me false, then I need to continue evaluating until I find a true. But if I call x.test and it tells me true, all I need is one true. And the whole expression is true, even if there are 50 terms. So this is an example of actually, lazy evaluation. Okay, it's called shortcut evaluation in the context of Boolean expression. So we have that. And we only call the methods that we need to call in order to find a solution. So that's really the definition of lazy that we used, okay? Second example, let's say we call a method, and the argument to that method are the result of calling other methods. That happens quite often, in regular programming. So my first argument is obtained by calling work method on X, the second by calling work method on Y. So the idea is that in Java, we use something that's called eager or applicative order for evaluation of argument, which means in Java, we know by the definition of the language that x.work is going to be called first. So the arguments are always evaluated left to right, and they are all evaluated before we call the method. So we call x.work, we call y.work, we pass the result to something, and that's it. That's the order that's guaranteed. Okay? Now let's look at something a little bit more fun. Let's look at, we are now passing methods as argument to other methods. So we're past lambda. Okay? So here's a predicate of string called my lambda. I assigned this lambda expression here. You remember that. We've used it in previous examples. And then we have a result variable that's going to be a list of string. We take our good old friends collection, we stream it, we filter using my lambda, and then we collect the result into a list. Well, the key with this and what we're going to use is that that lambda here, when you write it, it's not evaluated. When you pass it, it's not evaluated. You pass it to the filter. The filter doesn't call your lambda right away. It's going to store that code and execute it only when it's needed. Execute it with a delay. So we can try to generalize this, and look at a larger code example, if you will. So we have a public class evaluation here, inside of which we have an evaluate method that returns a Boolean. And really all it does is you give it an integer and it evaluates if that integer is greater than 100, true or false. That's all it does. But then we add some time-consuming operation in the middle, to make it like long to execute. So based on that actually class and the way it works, we can define a static method eager evaluator, right? That takes two parameters which are Booleans. And then all it does is display some blah blah on the screen and displays the result of doing the logical AND between the first parameter, and the second parameter. So let's call eager evaluator and pass as parameter a call to evaluate of 1 and evaluate of 2. Okay? Let's see what happens. So the rule that I described applies. So we call evaluate of 1. So it displays on the screen a trace, okay, telling us what that happened. Then we call evaluate of 2. Once we have the result from the evaluate of 1 and evaluate of 2 calls, we use them as argument to eager evaluator. Eager evaluator, we enter the code here, and we determine, whether the two results here were false, so false and logical and false, we determine that the outcome is false, and we're done. And that is the traditional way that Java works. So now we are going to see how we can be lazy by using lambdas. Okay? So let's take a look at this version here, that lazy evaluator. Instead of accepting Boolean value as parameters, which causes Java to evaluate all the parameters first, I'm going to say I'm going to accept a supplier of a Boolean value. So I'm going to accept something that at some point is going to be able to give me the Boolean value that I need when I need it, as opposed to, before even to start executing that method. That's the key. Okay, we saw that lambda are not executed immediately. So this is a lambda, this is a functional interface. How are we going to use that? Well, we don't have to create, more stuff. I mean, technically we do create more stuff, but it's done on the fly with that neat, beautiful, elegant lambda expression notation. So instead of passing the result of calling evaluate 1, I pass actually a supplier of Boolean that is a lambda that say, well, whenever you feel like it, call me the lambda, and I will then call evaluate 1 for you and get you the result. That's exactly what it means. So we pass those two lambda, and what is the result? Well, Java evaluates this first argument. It's a lambda expression, so it results in a lambda. That lambda is passed in this argument here, this parameter here in 1. The second one is evaluated. That expression results in a lambda. The lambda is passed into. Evaluating a lambda doesn't mean executing it, okay? And then lazy evaluator is called blah, blah, blah on the screen. And then we call here, we try to evaluate this Boolean expression. So how does it work? Well, we already covered that shortcut evaluation, right? So I call in1.get. So I say, I need my Boolean value now. You're a supplier of Boolean, give me my Boolean value. Well, fine, okay, so now the lambda is going to call evaluate1 and return whatever evaluate1 return. So this is going to be my first Boolean value. And then it turns out this Boolean value is false, so we just avoided doing works we didn't need. So you see, instead of calling a method, we encapsulate the call in a lambda. Well, that's not the word I should be looking for, but we encapsulate the call into a lambda so that it can be actually done later only when you need it. Okay? All right, so I'm going to stop here. I still have one more thing to go over in the slide deck, but we'll do it after the break, next session, okay? And we'll do our little review of concurrent programming. So I'm going to stop the recording real quick so that I can start the upload before other people start coming into the classroom. But if you have questions, I'm not moving, I'm not going anywhere. So I'll be here.